In this video, I will discuss nuclear magnetic resonance spectroscopy, referred to as NMR. NMR is the most powerful method you're going to learn about this semester for determining structural information about a compound. It is the most common method used by organic chemists. It is a form of spectroscopy because it involves an interaction between electromagnetic radiation and the nucleus of an atom. In this course, we'll focus on carbon and hydrogen. However, there are many types of NMR spectroscopy, including fluorine and phosphorus NMR. Importantly, the information we get from the NMR will help us figure out how the carbons and the hydrogens are attached to each other. Let's go back to general chemistry and look at the concept of spin because it's important here. So protons and neutrons in a nucleus behave as if they are spinning. And if an atom has an odd number of protons and/or an odd number of neutrons, it will have what's called a net nuclear spin. The examples of atoms that will have a net nuclear spin include H1, the most common isotope of hydrogen, carbon-13, nitrogen-15, fluorine-19, and phosphorus-31. The spinning of the nucleus creates a magnetic field called the magnetic moment. So here is an animation of a nucleus spinning on its axis. So as that positive charge is spinning, it's going to create a magnetic field around it with essentially a north and a south pole. Now, in any given sample, the nuclei are spinning in random orientations. However, when you expose these nuclei to an external magnetic field, they will align either with the field or against the field. So notice that the direction of these vary. Some are with the field and some are against the field. So here is an illustration of the magnetic moment which exists perpendicular to the axis of nuclear spin. So typically, magnetic moments of atoms are disordered. However, if they are exposed to an external magnetic field, which we often represent as B naught, B sub 0, their magnetic moments will align either with the field or against the field. So a magnetic field has a direction to it, and if these magnetic moments are in the same direction, they're parallel and they're with the magnetic field, and if they're pointing in the opposite direction, that would be considered against the magnetic field. Nuclei whose spin opposes the external magnetic field are in what's called the beta spin state, which is the higher energy spin state. Those that are aligned with the magnetic field are in a lower energy spin state called the alpha spin state. So see here with the direction of the arrow that those in the alpha are pointing in the same direction as the applied magnetic field, where those called beta are pointing in the opposite direction of the applied magnetic field. When an atom in the lower energy alpha spin state is exposed to radio waves with just the right energy, photons are absorbed and the spin flips up to the higher energy beta spin state. This energy gap is determined by the strength of the external magnetic field. The stronger the external magnetic field, the greater the energy gap. Now let me introduce a concept called shielding. So I mentioned the nuclei having a particular spin that's aligned with or against the external magnetic field. Now let's talk about electrons. So the external magnetic field causes electrons in your molecule to circulate, inducing an opposing magnetic field. So the induced magnetic field opposes the external magnetic field. Nuclei then experience less of an external magnetic field and are said to be shielded, which then requires less energy to undergo the spin flip. Nuclei surrounded by less electron density are said to be deshielded. Therefore, the amount of radio wave energy necessary for that alpha to beta energy transition depends upon the electronic environment of the atom. And this is how we're going to get information about our compound. When the alpha spins are flipped to beta spins, energy is absorbed and the atoms are said to be in resonance. This is the resonance part of NMR. The amount of energy required for a proton to spin flip tells us about its electronic environment and thus the structure. And note that resonance here is different from the types of resonance structures that we've drawn in the past. This is a different type of resonance. So this picture shows that depending upon the strength of the external magnetic field, the energy gap between the alpha and the beta spin states changes. So Tesla is a measurement of magnetic field strength. So at a lower magnetic field, this energy gap is smaller. At a higher magnetic field, this energy gap is larger. That means that for a stronger magnetic field, you need more energy to flip alpha spins to beta spins. The strong magnetic field in NMR is created when a high current is passed through a superconducting material at extremely low temperatures. The greater the current, the greater the magnetic field. And these low temperatures, approximately 4 Kelvin, require that we use liquid helium to cool the instrument, and that is typically then surrounded by liquid nitrogen to further keep the helium cool. Radio waves are used to excite the sample, which is going to facilitate the flipping of the spins from their lower energy to their higher energy beta states. Each of the atoms is excited and then it relaxes, and when it relaxes, energy is released. And then that energy that's released is recorded as a free induction decay. This FID then undergoes a mathematical treatment called Fourier transform, which separates the signal so we can see the individual signals for each atom. To actually do this analysis, you prepare your sample in a liquid solution using a deuterated solvent. That's just a solvent where all of the hydrogens are replaced by deuteriums. And then you place that solution in a small NMR tube. The sample is then placed into the instrument where it is then exposed to the magnetic field, and the tube is spun at a high rate to average magnetic field variations. This is a very simple illustration of an NMR. So you would insert the sample here, and then the sample tube will spin within the probe and be exposed to the magnetic field. Then you have a radio frequency generator and a computer operating console, and the Fourier transformation of the signal occurs in the computer. And this would be an example of a deuterated solvent. So that's deuterated chloroform, where you've exchanged the hydrogen for a deuterium, which is an isotope of hydrogen. The reason that we use deuterium is that it will not have a net nuclear spin, so it will not give rise to a signal in the NMR, which would just be overwhelming the signals of the compound that we're trying to analyze, because there's always more solvent than your compound. Primary focus in this class is to interpret NMR spectra. And NMR spectra contain 4 key pieces of information. 1, the number of signals. 2, the signal location, also called the chemical shift. The signal intensity, also known as the area under the signal or the area under the curve. And the signal shape, which tells us about the splitting pattern. Shown here is an example of a proton NMR. So on the x-axis, we have the chemical shift, which is recorded in parts per million. And then these would be your signals here. The number of signals indicates the number of different kinds of protons. And figuring out how many signals a compound will have requires you to look for symmetry in a molecule. So let me start with defining some terms: homotopic and enantiotopic. So identical protons are chemically equivalent, and they can either be homotopic or enantiotopic. Homotopic protons exist if the molecule has an axis of rotational symmetry that allows one proton to be rotated onto the other without changing the molecule. So these protons in red are example of homotopic protons. So if you flip this over, the H's exchange place, but you cannot tell one from the other. And the same is true of the other H's and the other two molecules. And it may help at this point to use a model kit and actually build these models and prove for yourself that there is an axis of rotational symmetry. So if you rotate around an axis, do you get the same molecule out? Another test is to simply do a replacement. Take one of the hydrogens, if you're not sure if they're homotopic or not, replace it with a deuterium, and then take the second hydrogen and replace it with a deuterium. If the resulting compounds are identical, then the protons that you replaced are homotopic. So in this case, we replaced that proton with deuterium, and then we replaced the other proton with deuterium. These two molecules are the same. This molecule on the right is the molecule on the left, just flipped over. And if you just flip something over, and you get the other molecule out, that means they're the same molecule. Enantiotopic protons exist if the molecule has a plane of reflection that makes one proton mirror the other. So with homotopic, you had to have an axis of rotation. With enantiotopic, you need a plane of reflection. So if I bisect this molecule with a mirror, then I see that this hydrogen mirrors the other. However, if I tried to rotate it, I would not get the same looking molecule back because the chlorine would come forward and the fluorine would go backwards. So there is no axis of rotational symmetry here. The same with this molecule. These hydrogens, if I have the mirror plane going through the molecule like this, these hydrogens reflect each other, but there's no way to rotate this molecule and have them exchange. You can also do the replacement test just like with the homotopic protons. So replace the first hydrogen with a deuterium and draw what you get, and then replace the second hydrogen with a deuterium and draw what that gives you. And then look at what is the relationship. Are they the same compound? No, because one is the R compound and one is the S compound. In other words, they're enantiomers. So therefore, those hydrogens must be enantiotopic. Now, what about if you do the replacement test and it produces diastereomers? In that case, the protons would be diastereotopic and they are not chemically equivalent. And we care about this because chemically equivalent protons give rise to one signal, whereas chemically inequivalent protons give rise to separate signals. So since both of these hydrogens are diastereotopic and they're not equivalent, they would each give rise to their own signal. So consider this structure shown here, and let's look at these hydrogens. These hydrogens are diastereotopic, therefore they are not chemically equivalent and they will each give rise to their own signal. You could do the replacement test to figure this out. You could also notice that there's no way to interchange them by rotational symmetry or reflectional symmetry. Now, luckily, there are some shortcuts to identify how many signals you should see in the proton NMR. The two protons on a CH2 group will be equivalent if there are no chiral centers in the molecule. If there are chiral centers, they will not be equivalent. So these two protons are chemically equivalent because there are no chiral centers, and therefore they will give rise to one signal. These two are not chemically equivalent because we have a chiral center here, therefore they'll give rise to separate signals. The third shortcut is that the three protons on any methyl group will always be equivalent to each other. And then finally, multiple protons are equivalent if they can be interchanged either through rotation or a mirror plane. So if we look at this ketone, these hydrogens are equivalent to each other because they're a CH2 group and the molecule does not have a chiral center. And the same situation is true for those. But ultimately, all four protons are chemically equivalent because there is a plane of symmetry through the center of that molecule where the hydrogens on the right mirror the hydrogens on the left. So all four of those protons will give rise to one signal. So we're just discussing the number of signals you might expect to have from a particular compound. And that's where you want to look at symmetry, and we want to look at rotation and reflection and use our shortcuts to figure out how many signals to expect. Then the next question is, where are the signals going to show up on the x-axis? And that is the chemical shift. Now, in most NMR solvents, 1% TMS, tetramethylsilane, is used as an internal standard, and the chemical shift is found using this formula: the observed shift from TMS in hertz divided by the operating frequency of the instrument in hertz. So for benzene on a 300 megahertz instrument, the chemical shift would be as shown here. The hertz of the signal is different in different instruments, but the shift relative to TMS is constant. So regardless of the strength of the instrument that you're using, the chemical shift that you will get will be the same. The chemical shift is a dimensionless number because the hertz units cancel out. But the units for the chemical shift are often given as parts per million, which simply indicates that the signals are reported as a fraction of the operating frequency of the spectrometer. And most signals appear between 0 and 10 ppm. On the last slide, the chemical shift was 7.27 times 10 to the minus 6, so that 10 to the minus 6 is where the parts per million comes from. So then that would just be 7.27 ppm. There are a couple terms that are used that are artifacts of early NMRs that analyze samples at a constant energy over a range of magnetic field strengths. And now we do it the reverse way. But the low field strength term is called downfield, and the high field strength term is called upfield. So downfield refers to the left portion of the spectrum, whereas upfield refers to the right portion of the spectrum, the portion closer to 0. Signals that show up downfield are D-shielded. You can think D for downfield matches the D of D-shielded, and signals that show up upfield are shielded protons. So shielded protons required a stronger external magnetic field to be excited at the same energy as D-shielded protons. So shielded protons have a smaller magnetic force acting on them because the electrons that are surrounding those protons have, in the presence of the external magnetic field, their own induced magnetic field, which is opposing the external magnetic field, shielding that proton from experiencing the full extent of that external magnetic field. And as a result, there's a smaller energy gap between the low and high energy spin states, and therefore it requires less radio energy to flip the spin states. And therefore those protons are going to show up upfield versus protons that are D-shielded, which means they experience more of an external magnetic field, which means they require more energy to flip their spin state from the alpha to the beta, and those will show up downfield in this area. And there are tables of chemical shift data that help us to know where to expect certain protons to show up. So protons can be shifted downfield when they are adjacent to electronegative atoms. So if we look at methane here, it shows up at 1.0. So the hydrogens in red show up at 1 ppm. By adding a halogen iodine, that shifts those hydrogens to 2.2 ppm. If we add the more electronegative bromine atom, they shift to 2.7. If we add the even more electronegative chlorine, they shift downfield to 3.1. And if we add the very electronegative, the most electronegative element on the periodic table, to fluorine, then they show up at 4.3 ppm. So notice that the hydrogen signal shifted further downfield when an electronegative atom was attached. And that's because it is pulling electron density away from those red hydrogens, which essentially is de-shielding it. If we look at this series here, we see that by adding additional electronegative atoms also gives the same effect of moving the shift further downfield. In addition, the closer those hydrogens are to the electronegative atom, the more they feel that effect. So these hydrogens that are on the same carbon the chlorine's attached to are the furthest down field. These hydrogens are a carbon removed on the beta carbon, so they aren't feeling the effect as much. And then these hydrogens are far enough away, they really no longer feel the effect of that electronegative atom. So the electronegative atom has an effect, but only over certain distances. To predict chemical shifts, you want to start with the standard ppm for the type of proton. The methyl proton has a standard ppm of 0.9. For methylene, which is just a CH2 group, it's 1.2. And for a methine, which is a carbon with just one H attached and 3 other bonds, it's 1.7. Then you can determine the effect of neighboring functional groups. So if we start with the methylene base ppm of 1.2, if that is next to an oxygen, you can add 2.5 to get to the actual chemical shift of 3.7. If the methylene group, which has a base reference of 1.2, is next to oxygen of an ester, so notice this is of an ester, this would be of an alcohol or an ether, we add 3 ppm to get to a value of 4.2. So these are ways we can estimate the chemical shift. Experimentally, it may differ slightly from our predicted values, but it should be kind of close. And then the effect on beta protons is about 1/5 the effect on alpha protons. So the beta protons would be this proton, these protons, for example, and these protons. If your protons are in a carbon adjacent to a carbonyl, then we typically add 1 ppm to the value. So here that would give us a predicted value of 2.2. The actual chemical shift is 2.4. The last topic is anisotropic effects. When electrons in a pi system are exposed to an external magnetic field, they circulate and produce a magnetic field, causing diamagnetic anisotropy. So here is an example. So for example, if you had a benzene ring, and the electrons in those pi bonds, there's 3 pi bonds in the benzene ring, are exposed to an external magnetic field, they start to circulate, and that produces its own magnetic field. So as a result, the protons that are here on the outside of the ring experience the external magnetic field plus this induced magnetic field. And as a result, they are further de-shielded by this induced magnetic field. As a result, these protons will show up downfield. So these hydrogens in red are showing up here past 7 ppm. The result of this effect is similar to shielding for protons when they're on the inside of the pi system. So here the protons on the inside of the ring appear at -1 ppm, where the ones on the outside appear at 8 ppm. Here is a handy table of different protons and where we expect to see their chemical shifts. And this is a very useful tool when you're analyzing an NMR spectrum and trying to deduce what type of structure you have. So as a question at the end here, consider cyclohexanone, a 6-membered ring with a carbonyl. Tell me how many signals you expect. In other words, how many sets of chemically identical protons are there? And then tell me for each signal, what do you estimate the chemical shifts to be? That's all. We'll talk about this more in class and do lots of practice problems.